Hello, everybody. My name is Kyriakos Muratidis, and I will present the paper titled on M-impact regions and standing top K influence problems. This is joint work with Bo Tang and Mingji Han. So the top K query is a standard preference-based query that helps us shortlist the top options from a large set of alternatives. Imagine that we have a user who is looking for a hotel, and these are the available hotels. The hotels have attributes value and service, where the higher value that you see here in these cells, the better. Now, my user specifies his preferences in the form of a weight for value and a weight for service. Together, these two weights form what we call the user vector, whose job is to capture the user's preferences. If the weight vector includes these two specific weights, 0.76 and 0.24 for the two involved attributes value and service, then the score of a hotel is defined as its value attribute times 0.76 plus its service attribute times 0.24. This way, each and every available hotel is associated with a numeric score, and therefore we can shortlist the top K scorers as the top K result for the user. Now, our job in this paper is to decide what attributes a new product should have, let's say a new hotel, so that it attracts at least M of the users, meaning so that it belongs to the top K result for at least M of the users. The input to our problem includes a product set. In the previous example, that was a set of hotels. A set of users where for each user we know the user vector, meaning the weights that specify her preferences, and a positive integer M. Now, the MIR problem computes the maximal region R in the product space, inside which, if we build a new product P, it will cover at least M of the available users. So in this scenario here, we have a product set that includes hotels with two attributes. We have a user set that includes 4 users. Here we're listing the user vectors for each of them, each comprising 2 weights, one for value, one for service, and their individual K value. Observe that K can be different from user to user. Now, in this situation, if the input parameter M is set to 3, meaning that we wish to satisfy at least 3 users with a new product to be created, the output to our problem is this gray region. It means that the new product must be built somewhere inside this gray area. Now, observe that the output to our the output of our problem is a region within what we call the product space. The product space has an axis for value and an axis for service, so that each and every hotel, be it existing or hypothetical, is effectively a point inside this product space. In addition to solving our MIR problem, actually, we're also addressing 2 top K influence problems that were not completely resolved in the past. Let me explain. The first of this problem is the CO problem. Here, the question is what attributes a new product should have so that it is the top 1 option for at least M of the available users. As a secondary criterion to satisfy is that we want to also minimize the creation cost for this new product. Now, the creation cost is defined by a function that is monotonic to the attributes of the product. The existing solution, first of all, is specific only to K equals 1. And second, it takes very long to run. That is why the authors of that original paper propose a sampling alternative to the exact approach. Of course, the sampling method is not exact. Now, our work can help solve this CO problem in its general form, meaning for k greater or equal to 1. We can do that by first processing MIR, computing the region R, and then feeding this region R into an off-the-shelf optimization solver so that we find the cost optimal position where we should build the new product within this region R that our algorithms have produced. Actually, not only is this approach exact, not only it applies for general K2, but even for the narrow K equals 1 case, it is at least one order of magnitude faster than the exact solution in the original paper that proposed the problem. The second standing problem that we apply to is the IS problem. The situation here is that we have an existing product P, which we need to upgrade so that its updated version P prime covers the maximum possible number of users from a known user set, subject to a given upgrade budget. Now, here the assumption is that to upgrade a product, we need to pay an upgrade cost that is again monotonically increasing to the attribute increment, similarly to the previous cost function that we had in the previous slide. Now, the existing solution is heuristic. It's a greedy algorithm, which of course is inexact. What we show in our paper is that we can adapt our advanced MIR algorithm into a branch and bound form that can solve the IS problem exactly for the first time. And as a matter of fact, to do that in practical response time. We also have an important side contribution. To our knowledge, the database literature on top K related problems so far has only considered synthetic preferences. Well, in this work, we have applied an established data mining approach in order to mine user preferences from actual TripAdvisor reviews on real hotel ratings. So using this mined user set and product set, we're getting that many users and that many hotels as shown here. And for the sake of example, I'm also showing you how the output of our MIR problem looks when we isolate two dimensions from the TripAdvisor dataset. We use k equal 10, and the target number of users to cover is half the users. So when we use dimensions, location, and room, this is how it looks. When we use front desk and cleanliness, this is how it looks. If I were to mention an interesting observation here is that in the location room space, there is a higher degree of correlation, which actually leads to a larger MIR result, a larger region that you see shaded here, and fewer existing hotels falling inside that region. Let's start by a naive approach to address the MIR problem. Let this value be the top kth score for the user WI. If we want the new product we will build to enter the top K result for this user WI, we must ensure that the score according to WI is greater than this value here, than this top kth value currently, which actually is a constant. Now, the representation of this inequality here corresponds to a half space in our product space. It means that it splits the product space into two parts. In one of the two, if the new product P is built, then it is guaranteed to enter the top K result for that user W1. We call this half space the influential half space for the specific user W1. So the naive algorithm proceeds as follows. First of all, it considers all possible combinations, m-sized combinations of users. In other words, it considers each and every possible m-sized subset of our users. Then it computes for each such subset the region of the product space where a product has to be built in order to satisfy all these M users in the subset. It does that by generating the influential half space for each of those users in the subset, and then taking the intersection of their influential half spaces. After having done that for each and every possible M-sized subset of users, then it takes the union of all the regions that correspond to each of them. While this is theoretically correct algorithm, it is impractical. It is too slow. So one step towards something more efficient is the baseline solution. So what happens here is that we get the influential half space for each user, and we insert it one by one into our product space. This means that we effectively keep dividing our product space with one by one each of them of the influential half spaces of our users. To maintain the resulting partitioning, we use an established data structure, which is called the cell tree. So the cell tree looks something like that. Effectively, it's a binary tree whose height increases by 1 after inserting each of the half spaces. Now, as we keep inserting influential half spaces one by one, we may encounter some partitions that already are found to cover the desired number of M users, meaning that we might find partitions like this R10 here that corresponds to this cell C10 that already are found to be included in enough influential half spaces. So these ones are early reported, meaning that we just output them and we don't bother with further splitting them. Similarly, it is possible to have some partitions, respectively cells of the cell tree, that are already excluded by far too many half spaces, so that even all the remaining half spaces to be inserted would include it, they would still not be enough to meet the target M. In other words, we can early report some of the partitions, some of these cells, and not be bothered with them as we keep inserting more influential half spaces. So at the end of the process, all the cells that are found to be included in M half spaces are being output to our application. So the complexity of this baseline approach is this one. This is the total number of users. This is the number of dimensions. This is quite huge and actually corresponds to the complexity to build the complete arrangement of as many half spaces. So we have a dual objective here. We would like to enhance the effectiveness of early reporting and early elimination, and would also like to keep the size of the arrangement as small as possible. This, by keeping the size of the arrangement small, we make the operations on the arrangement also faster. So a central idea that we'll use is a grouping idea. So we group our users according to their kth product, so that users that have the same top kth product are forming a group. I'm visualizing here such a situation where I have 5 users whose top kth product for all 5 of them is product R. This is visualized here, and you can see what happens. All the half planes that define the influential half spaces for these 5 users are guaranteed to pass through this product R. Now, this product R can be used to quickly identify cells, meaning partitions of the product space, that are guaranteed to be inside each of the influential half spaces in the group, like it happens here. And we can do that by comparing to this common product R and some carefully chosen half spaces here. I will skip the details. And similarly, we can quickly identify some cells, meaning some partitions of the product space, that are guaranteed to not cover any of the users in the group. So if we suppose that M is 5 and the total number of users is 9, in this scenario, we would already be able to early report C1 because it covers all 5 users of this group, and we'll be able to early eliminate C2 because it's guaranteed not to cover any of the 5 users in this group, and therefore it will never hit the target of m equals 5. So the question is, what happens with situations where this grouping cannot help us directly figure out that the entire group covers or doesn't cover the specific cell? Well, in these cases, we need to look deeper into the individual users of the group and classify them into a cover set, meaning those whose influential half space completely covers that cell, those that cut through the cell, just like these dashed ones that are shown here, and those that completely exclude the cell, this specific cell. Now, to do this classification, we need some geometric operations, right? So it is one viable way to improve performance to actually expedite this classification. And luckily, we're able to do that. Imagine that we're having a set of users, and observe that here I'm referring to the weight space. So every user vector is actually a point inside here, okay? So imagine that we have a group of these 15 users, and we know that W1, W2, and W3 are covered by any product within a specific cell. The same is bound to happen, the same is bound to hold for the user W10. This means that in a more formal way, that every user that is in the convex hull of these 3 is guaranteed to also be covered by any position within the specific cell. The same holds in the case where W8, W7, W6, and W5 do not completely touch on the cell, meaning completely exclude the specific cell. The same is bound to happen for W13 and W14. So this can help us do the classification that I explained in the previous slide into these 3 groups faster. Furthermore, that classification and this observation can also help us in a delayed processing of the half spaces, of the influential half spaces of these in-between users who cut through the cell C. So instead of just partitioning the cell according to all 5 of them, we just take those in the convex hull of these black users. So we only partition a cell, the cell in question, let's say C, according to the influential half spaces of W4, W12, and W9, and we're getting these partitions. These 2 users, W11 and W15, we defer their processing later, further down the road, so that if some processing of other users may eliminate some of the produced cells here, we will actually have saved the effort to go ahead and eagerly also partition according to W11 and W15. Observe that there may be multiple groups of users we need to process, right? Each user has the same common top kth product. Therefore, in the general case, we have multiple groups of users. So in addition to these optimizations, there is also some simple geometric trick that we can play by approximating the different cell regions by MBRs, for example, in order to expedite in a fast filtering way some geometric operations. And that can actually, although it is simple, it can actually save a lot of time. I need to mention that special versions of the algorithm are possible for the 2-dimensional case, but I leave the details for the paper. And also here I'm showing you some examples of performance measurements, just to show you that performance is practical and reasonable. And here you can see that as the number of K increases, the number of groups also increases. and the average size of the groups also decreases. For more details, I have to refer you to the paper. Thank you very much for attending the presentation.